Good afternoon, and thank you very much to our session 2 participants. That was a very spirited discussion and very impassioned. So thank you very much. We all learned a bunch. We now come to our third session this afternoon, and it's I think something that'll be very important to our practitioner community here, and it's a review of statistical and machine learning ideas and methodologies that promise to impact the practice of systematic investing. And we're really fortunate today to have an outstanding roster of professors that have a particular focus in this discipline. Starting out, we have Emmanuel Candes, and Emmanuel comes to us today from Stanford University, where he is a professor of mathematics and statistics and the Barnum-Simons Chair. We thank you for being today. Also with us is Jun Liu. Jun comes to us from Harvard University, where he's a professor of statistics. And also with us today is Panos Toulis. Panos comes to us from the University of Chicago Booth School of Business, where he is an assistant professor of statistics. I appreciate all of you joining us today. Very excited for this panel. And Ed, I'll turn it over to you. Thank you.
Thank you, John. I would also like to thank our distinguished presenters here on behalf of the Statistical Science Department at Temple University. Thank you for being here, everyone. So like John mentioned, this session is going to be focused on ideas and tools for systematic investing. And we have roughly, a third of our participants from the industry sector and a two-thirds from the academic community. So for people who may not be familiar with systematic investing, the signal-to-noise ratio in this situation is typically very low, even lower than in computational advertising and AdWord type auctions. So methods to tighten the error bars are typically of interest, and especially new ideas that are somewhat model-free, because it's always easy to tighten the error bar assuming a model, but that's typically a fatal mistake in a lot of applications. This is the topic of today's panel. Variable selection independent interactions, multiple testing, method that could navigate bias, variance trade-offs, penalize estimations. So we'll explore some new ideas in this space. So in our content library, we have a list of papers by the speakers and also related papers. Recently, Emmanuel Candes put forward the idea of knockoffs. And you can read about knockoff filters on the page that's linked. And in June, even more recently, has been further innovating by introducing a techniques based on data splitting that is leveraging some of these ideas. So I'm going to turn it over to June. June, go ahead. Thank you for being here today.
Thank you very much. Thank you, John, and thank you, Edo, for the nice introduction. It's a great pleasure to be in this panel. So this work is some of our recent progresses. It's completely inspired and also stimulated by the work of Emmanuel Candes, who I guess has moved on somewhat, but a lot of his followers are still working on this related problems. It's very interesting, and also another aspect that motivated us was exactly as Edo mentioned. We try to be more model-free in some sense, but it's always their price to pay. Anyway, okay, so I will, next slide, please. This is collaboration with a few of my students, and I will introduce the FDR control stuff, assuming many of you may not be familiar with the topic. And then I will mostly focus on data splitting ideas. It's actually pretty straightforward in terms of the approach. It just split the data and then do things to create independent confirmations of each other. Okay, next slide. So one of the fundamental concepts of this FDR control was introduced by this landmark paper by Benjamin Hochberg, who are thinking about scenarios where you have many independent hypothesis testing tasks to do. It's just one setting. There are actually many related settings in bioinformatics, in finance, and so on. Basically, you can regard all, there are many different evidences, different so-called signal-like observations, but you want to really discern which one is true signal, which one are noise. So you can formulate them as a p-value problem or the hypothesis testing to test whether the means are non-zero or zero. So the one of the most celebrated or simplified version is the normal means problem. You have a sequence of independent normal observations and with potentially different means and different from zeros, and you want to figure out which one is not zero. So typically you can use p-values and the next slides. And their procedure is to, next slide, please. Is to actually order the p-values and then draw a line which is controlled by the so-called FDR rate. Suppose you want to control the error rate at 10%, 0.1. Then after you order these p-values, you just draw this red line which is touching the other side at 0.1. And then whatever hypothesis p-values under this line will be selected. And you can prove that the false positives below this line, well, for your selection is somewhat controlled at the level. So this can be proved by when it's independent, but when they are correlated, there are some price you have to pay. And if they're not too correlated, this is almost correct. So, but if they're too correlated, there could be trouble. There's some relaxations. Next slides. Next slides. Oops. Yeah, so here we are thinking about the situations where there could be correlations. That is, we are thinking about regression scenarios. This could be high dimensional or moderate dimensional, but P is usually very large. So I saw in some finance data why this P could be a few thousands, and number of observations could be hundreds of thousands. And in some biology data, it's a little reversed. The P could be tens or hundreds of thousands, and the N could be a few thousands. So there are situations both ways, and they're both real, and actually very, very, very much real. Very many people are interested in getting something out of this type of data. So we're interested in doing model selections in some sense, and one approach is to do simple regression or some kind of a penalized regression and trying to decide whether you have selected the right predictors or not. So the notation-wise, we think about say S0s are those coefficients corresponding to zeros. Those features coefficients are having been zeros, and S1s are those non-zero coefficients that. Our goal is to figure out which one belongs to S1, but we try to include as fewer from S0 as possible. And the so-called FDR control is to control that in your selection, the percentage of the variables you selected from S0 is bounded by a rate Q, or in probability, or in some asymptotic sense. We all will talk about. And we mostly will cover the linear models and some graphical models, and also some generalized linear models, and trying to see this data splitting approach, how it works. Next slide. For FDR control in the regression model, there's some early works based on this Benjamini Hodgkoff's procedures. Although these p-values are correlated, if they are not too highly correlated, their original procedure works pretty well. So especially in dimension when p is relatively small compared to n. But when p is becoming comparable to n, then the problem may occur when they're somewhat correlated. And there are some different extensions, but the extensions typically are different ways of coping with correlations, but they tend to be very conservative based on this modified BH procedure. There also early work on data splitting, which is to use the first half to do to find variables, and then you use second half to set up a p-values, and then you use that to do variable selection. That's still reasonable. So this approach is useful for high dimensions. But as you can see, once you do data splitting, you sort of weaken your signal in this case. So that's somewhat one price you have to pay. We hope later on I will try to see if you use multiple data splitting approach to aggregate all this splits information, you actually can get back the almost full information. The recent revolution was, as we all mentioned, by Immanuel Candice group, and they have developed a very innovative ways of doing this variable selection. I think, to me, there are sort of two key ideas from this approach. The general idea is to create fake variables. And the consequence of creating these fake variables, there are two. One is so-called self-referencing, meaning that you don't really need the p-value to tell you whether it's good or not or bad. You can do so-called self-referencing. For if it's a null variables, this particular variables, because of the knockoff, should show some kind of a symmetry around zero behavior. And another one is somewhat make this kind of information independent. Next slide. So this is a brief introduction of this knockoffs in 2014 paper. They have many different variations afterwards, so I have no way to cover all of them. But interested people, please check their websites. They're very interesting progresses. And here is just say you can think about this pictures. The left is the real variables, the right is the fake ones. You create exact copy, not exact copy, sort of a fake copy with the exact size of the original X. And one way to make them is to make this particular covariance matrix design. And in this way, you can guarantee the so-called exchangeability things. There are a few approaches. One is more efficient than others, and over the years, people have had some nice progresses along this direction. But this is rough idea. And in low-dimensional case, you could do this exactly without assuming anything about the X. But in high dimensions, you may need to assume some joint distribution of the X's, or at least up to some nice exponential families. You have to make some assumptions in that way. The next slide. So this is the fundamental of self-referencing. That is, if it's a null variable, you create this statistics based on either knockoff or we do data splitting, so that under the null hypothesis, this is symmetrically distributed around zero. So this is marginally symmetric. So that's one thing. And also, so we mostly utilize this. Another one, as I mentioned, is somewhat the sign independence. That one we cannot achieve anymore because of the correlations. So another effect we would like this to have is the so-called signal strengthening. This is hard to achieve, but at least don't do too much signal weakening when it has a signal. So this is related to the optimal way of constructing this this particular statistics. Next slide. So the data splitting approach goes as follows. You just split the data into equal half, and then you can estimate sort of two coefficients, and we generally call the impact measurements. Really means if you are actually doing the neural networks, you can still measure these things, but it's no longer coefficients. It's really the influence functions. And then you can construct this mirror statistics by, I think this is pretty general. I don't know whether this is the most general forms, which is the sign of these two coefficients and multiplied function of the absolute value of the magnitude of these two coefficients. There are some typical approaches, the most straightforward is this -1, but this turns out to be less efficient. There are more, I think this one was first observed to be relatively more efficient in the original Candice paper. And recently, some of my colleagues, Tracy Cook, they have done some work to prove this is optimal under certain case. You can also think this is somewhat optimal from hypothesis testing. If you use Neyman Pearson lemma, you sort of can argue this is the best. If you think about this, this data splitting create these two copies of the beta estimates. And if you look at two-dimensional, they're just spherical Gaussian asymptotically. So if you do sort of hypothesis testing, optimal boundary will be just like this one. So it's not hard, but I will not give you details. The next slide. So once you have this kind of symmetry and you require something, so heuristically, you just need to use the negative tails to account for the false positives. So imagine you are cutting off at the boundary, which is tau, which is the statistics is tau. And those true signals tend to be large, positive. So that's on the red part. And the blue parts correspond to the false positives. You of course don't know which one is belonging to the blue part, but you can use the negative tail to estimate this amount. So that's the idea of knockoff, and this also the self-referencing, and the same here. Another thing we sort of need to assume that this individually is fine, marginally is correct, but if you want to accumulate them, like sum of all these quantities, you need somewhat weak correlation assumptions, which typically can be satisfied in high-dimensional linear models. And if you want to prove some asymptotic properties, those standard assumptions usually can imply this type of weak correlations. But even when they are highly correlated, as we tested, they still work, but we can't prove it anymore. Next slide. The multiple data splitting is also, as name suggested, you do this multiple times, and then each time you will have a collection of variables being selected, and then you try to assemble them together to get the coherent ones. The next slide. The next. So the way we assemble them is slightly different from what people have done for data splitting. And this one we introduce the so-called inclusion rate. That is, for each data split exercise, some were being selected, some were not. So suppose we only selected 100 out of 1,000 variables, and then each selected variables will give a weight of 1/100. That is 1 over the number of selected variables, and all the others will be 0. So for each selection, the total inclusion rate is exactly 1. So then for those variables, they tend to be selected more. So if you accumulate their selection rate, take average, they tend to be large. So you can order them according to this inclusion rate. And then you can cut off at the smallest ones at a certain level so that they sum up to Q. We can actually prove under some asymptotic property that this is pretty conservative. And if the single data splitting can keep this control, this FDR control, then this multiple data splitting will also be able to do that. And actually it's slightly better than the single ones, but how much better we cannot really quantify. So next slide. So this is illustration of this multiple data splitting effect. So this is very simple normal mean problem. So in this case, actually, the p-value is the perfect summary of the statistic. That's what we call as the full information. You can imagine you do the data split, you split in half, and you do this kind of mean estimate contrast. If you do one data split, it's very noisy, right? Because some by chance will be large, some by chance will be small. So if you look at this scattered yellow dots, these are sort of one data split. They sort of, this score are all over the place. They're very non-concentric. But if you replicate this many times, you can see this is the p-value. They're almost monotone functional p-values. So that's nearly perfect recovering the full information. And these just illustrating the blue dots are those resulting from like 10,000 replicates. And this orange dots are 400. 400 is pretty good. In practice, we also compare the powers. Next slide. Next slide. So you can see that even with about like 400, 100, well, I don't have that slides, but usually with 100 to 200 data splitting, you can almost get saturated. You can't really get much more. So this is also power comparison for the normal mean problem compared to the this BH procedure, which is supposed to be the optimal in that case. And you can see this is almost indistinguishable. The blue one and also the gray one. So these are almost indistinguishable. The red one is the single data split. You can see clearly the power loss. The next slides. So for linear models, especially in both high dimensions, if it's very low dimensions, you can just do two independent OLS, the ordinary least square, then you do the contrast, that's fine. But if you have high dimensions, we usually suggest to do the lasso, but with relatively more loose lambda, but we want to be able to do to have so-called screening property, meaning you include all the relevant variables. And then you can use those selected variables from the first half of data to do the ordinary least square on the second half. Then you can construct this MJ for all the variables. And in this case, you can prove they are symmetric properties satisfied and so on. Another strategy is to use post-selection inference. You can also do that. We tried both. It seems to be not too much difference. The first one seems to be easier. The next slides. So we did some comparisons for different sizes of covariance matrix and compare with BH procedure and also the knockoff. As you can see, this is, I don't know how clear you can see. The top figures are FDR control. The nominal level is 0.1, so they seems to be all doing very well. And this block ones are some procedures from this Swiss group, and they tend to be very conservative. This one way of doing this kind of multiple data splitting things. You can see especially the weak signal case and also high correlation case, this multiple data splitting are doing well. So, but in relatively independent case and the strong signal case, the knockoff seems to be doing better. So that seems to be consistently observed in many different settings. Next slide. And this is a case where the assumption seems to be violated for almost all methods. This is reasonably high dimensions, but there's a constant correlation, meaning that all of them have equal correlation. That's the case. You can't, the correlation is really not weak. Eigenvalues are getting large. You can see this is the independent case. The knockoff is doing quite well. The MDS is not too bad. This is FDR control level. So the lower right corner will be better. So this one, the X direction is the power, the Y direction is FDR control. FDR levels, you want that to be low. And you can see in this is case where the correlation become large, 0.1. So MDS is getting lower FDR and also higher power in this case. The next slides. We also try some non-normal designs. This was the example has been tried in some of the knockoff literatures, which we used some correlation, the axis from this GWAS studies. These typically correspond to the SNPs, so they are not the continuous, they're actually discrete values. So it's not particularly normal, but they're not too bad if you have large enough, they're almost. So MDS is doing well in many cases, especially you can see the weak signal case. This is relatively weak signal case is doing quite well. So that's one thing we observe. We still don't understand why exactly this multiple data splitting works. Seems to be able to recover these subtle signals in the weak signal case. Next slides. This is some non-Gaussian designs. The covariance matrix are the axes are simulated from T distribution or mixture Gaussian distributions, and this is a little unfair for other methods because when you assume they're normal, then this is misspecification. They tend to have errors. But this is just trying to show that multiple data splitting seems to be quite robust to this type of different design matrices. So you can see the MDS for this blue triangles, their FDR almost always under the control. Next slides. I don't know how much time do I have. Next, yeah, this is graphical model. I won't
give about 5 minutes.
Yeah, next slides. Yeah, this is just result. Next slides. So this is about interest. I just want to mention this generalized linear model case. It's also inspired by, also stimulated by Candice's work. And as you can see, both of these works actually were communicated very clearly and very excitingly by his very fabulous students. One is this Pragya Sir, and another is Lucas. Lucas Jensen. I mean, so both of them were hired recent years, and then during their talks and their casual conversations, so we got quite stimulated, and especially my students were very excited to learn these things. And this is also a recent work. They found that in the moderate dimensional case where P and N are of the same order, so that's the P over N is converging to some constant between 0 and 0.5. And then the asymptotic results for the MLE in the nonlinear, in this generalized linear model is no longer the classic one. There's somewhat a rescaling effect. In other words, the center will be rescaled compared to the truth, and the standard deviation will also be rescaled. So this creates quite some issues and problems in the classic inference. If you want to give a confidence interval, even asymptotically correct the confidence interval is not very easy to get because of this very tricky normalizing factor, alpha star and sigma star here. But we can actually using data splitting to do this without worrying about alpha star and beta, sigma star. Of course, we will not be able to give a confidence interval, but we can actually do this variable selections quite well, because under the null, beta j star is 0, that's the true beta. Then the only unknown factor is sigma star. But sigma star, if you only use the symmetry property, not the scale property, then it's okay. So we actually are completely fine without knowing that if you're just creating a mirror statistics. So that's how it works. So the next slide. So if we use the data splitting, it works quite well. So this is the large P and N. And also this ABHQ is the adjusted procedure using p-values. That's actually adjustment based on this Candice and the Sir's results to adjust the correct scales, then it works the best. So BHQ has FDR out of control, so this gray squares should not be counted. But the best one, which is still under the control, is this ABHSQ. But you can see MDS is actually not far. It's very closely matching the results in this particular case. And also the next slides, in the case like in some other models, negative binomial, I don't think so far we have known these rescaling factors. So there's no nice papers. Maybe Emmanuel already had a new paper on that, but that will be a different formula. But in this case, the MDS is still doing quite well without having to know that. The last, okay, next slide. So in the high dimensions, of course, we can do this so-called debiasing lasso. But somehow this debiasing lasso achieve asymptotic normality rather slow, but it achieved the symmetry rather quicker. The next slides. So this is the picture. So you can see if you use the normal p-value, it's pretty bad. That's the right top angle. But if you just use the symmetry to create this contrast statistic, they are quite symmetry around 0. You can see the right lower figure. So because of this, if you use the data splitting to do contrast, it's actually doing quite well. The next slide. The MDS shows very good power compared to other methods. The knockoff somehow in these cases are not doing very well, but I don't know exact reasons. Anyway, so I probably, the next slides. Yeah, we tried a real data example, which has been analyzed also by Candice group. This is microarrays and trying to figure out which genes are particularly responsive in this different types of treatments and so on. So the next slides, I just don't have time to give you much details, but here is just the genes we selected, and the top half were also selected by knockoff. So we selected a set which is the superset of the set selected by knockoff. So basically double the size. And the right columns are some literature supports for the findings. There seems to be some support for our findings in this case. It's not completely sure yet, but it's somewhat sign support. Okay, so the next slides will be, well, I think it's an interesting work. I don't want to read through that, and it's stimulated by the great statisticians like Vin and also Emmanuel's group. And next slide, I'd like to acknowledge, so Lucas has been quite instrumental in stimulating us to think about this. And also Binyu's talk on this data perturbation has been quite also stimulating. Let's give us some basic ideas. So there are quite a few collaborators on this work, and they're all young and energetic. Thank you very much. I will stop here.
Thank you, Jun. Very interesting work. It seems like multiple data splitting is both reasonable and powerful, especially as the independence assumption fails and as you move to moderate to stronger correlations of the signal. So something to try out for sure.